Hi, I am Dr. Neeraj Upadhyay again with you for discussing our next module titled Crystal Field Theory for explaining bonding and application of coordination compounds. Dr. Bhavana Sethi is the co-author with me in this module. In the last module, we have discussed about the valence bond theory approach for explaining bonding in coordination compounds. There, you get to know that central metal provides vacant orbitals equal in number to the available field or sigma orbitals provided by the ligand. All these vacant orbitals hybridize to produce equal number of equal energy orbitals and then overlap with the available sigma orbitals of the ligand. Since there were possibilities of participation of inner as well as outer d orbitals in hybridization, therefore, the model suggests to chalk out the participation of inner or outer d orbitals by finding value of experimental magnetic moment and comparing with theoretical value of the spin-only magnetic moment. The theory is easy to grasp and apply, but is having serious limitations, like theory is lacking in understanding the properties of coordination compounds like color, magnetic properties, etc. Even sometimes there it becomes difficult in finding participation of inner orbital or outer orbital in hybridization if value of magnetic moment fails to explain that. Also, the model did not contain any quantitative aspect and unable to explain the stability of the coordination compounds. It is therefore valence bond theory was thought to have limited applicability and a new, better theory was needed. During the period, crystal field theory emerged with larger applicability and more acceptability. Here, in this module, we will learn about assumptions and detailed explanation of crystal field theory. The learning objective of this module is to chalk out the assumptions of crystal field theory and their explanation for applicability in coordination compounds. The crystal field model has largely replaced valence bond theory for interpreting the chemistry of coordination compounds. It was first proposed in 1929 by Hans Bethe. Further modifications were proposed by J.H. van Vleck in 1935. It was a model based on a purely electrostatic interaction between ligands and the metal ion. That is, coordination compounds were thought in the direction of an ionic crystal lattice where the major force of interaction is electrostatic force. When a metal ion is surrounded by an ion in a crystal, there is an electrostatic field produced by the anions that alters the energy of the d orbitals of the metal ion. The field generated in this way is known as a crystal field, hence the name crystal field theory. The theory concentrates on the resulting splitting of the d orbitals into groups with different energies and uses that splitting to rationalize and correlate the optical spectra, thermodynamic stability and magnetic properties of the complexes. Now let's move towards the assumption of crystal field theory. The central metal cation of a complex is surrounded by ligands. The ionic ligand, that is fluoride, chloride, cyanide, etc. are regarded as negative point charge, while the neutral ligand, for example, water, ammonia, etc. are regarded as negative point dipoles, where the negative end of the ligand dipole is oriented towards the metal cation. A positively charged central metal has considered as positive point charge, while a neutral ligand metal atom was assumed as point positive dipole. According to CFT, there is purely electrostatic or Coulombic attraction between positively charged metal ion and negatively charged ligands. CFT does not consider mixing of orbitals of metal ion and the ligand. That is, it does not consider any orbital overlap. But to minimize energy of the formed molecule, ligands arrange themselves in different shapes that affect differently to different d orbitals, and therefore d orbitals split up. Let's explain the theory by taking an example of octahedral geometry. You all know octahedral geometry forms for coordination number 6, that is, in the specific example, metal M is surrounded by 6 ligand L. So, our generalized example is of Ml6, which may or may not be a neutral species. So, according to the theory, metal M is a positive point charge or positive point dipole, while ligands are negative point charges or negative point dipoles. The attraction between the two is completely electrostatic in nature. Therefore, initially, let ligands are situated at the infinite distance from the metal ion. According to basic assumption, lines of forces originate from cation, that is from metal, and falls onto the anion, that is ligand. The electrostatic force of attraction is completely responsible for the formation of chemical bond between the metal and ligand, and the bond energy can be determined by the formula bond energy equal to Q1 into Q2 divided by 4 pi epsilon naught R square. You all are familiar with this equation. Here Q1 and Q2 represents charges of cation and anion respectively, and R is the bond distance between the two. Now, the value obtained for the bond energy by this way does not match with the experimental value of the bond energy, specifically in the case where M is transition metal atom or ion. The difference between main group and transition metal is by d orbitals only. So, let us elaborate the electrostatic effect on d orbitals of central metal ion. So, when ligand was situated at the infinite distance from the metal, it gets attracted, and due to that attraction, energy of 5 metal d orbitals start decreasing till a certain distance. But at a certain point, electron present in metallic orbital feels repulsion with the incoming ligands by their charge. That increases energy of 5d orbitals. This equal increase in energy is, however, a hypothetical situation. Now, to minimize the energy of central metal ligand, ligands are orient themselves in a specific arrangement. For example, in case of Ml6, the arrangement is octahedral. So, let us understand the octahedral geometry and the effect of ligand on the metal orbitals. It is better to understand a three-dimensional model in terms of cubical room. The metal stay at the center of the cube and considered as origin of three-dimensional coordinate. The three axes x, y and z are pointing towards the corner of regular octahedron. In a cube, you can imagine the three perpendicular lines passing through the central metal ion as the three axes x, y and z. All the 6 ligands are approaching from the direction of these axes only and occupy the position of each of the face center of the cube. So, metal is at the body center of the cube and ligands occupy the position of all the face center of the cube. It is therefore, two ligands are approaching towards M on each of the axes but from the opposite direction. You can see this in model shown here. As you can see, all the 6 ligands in the octahedral geometry are interacting through axial position. When ligands approaches a certain distance from the metal orbitals that occupy electrons start getting significant repulsion from the incoming ligands. The orbital S is spherical and P orient in px, py and pz axis, and therefore, the energy of all these orbitals increases equally. But the same is not the case with the d orbitals. D subcell is formed by the combination of 5 d orbitals, that is dxy, dyz, dzx, dz square and dx square minus y square orbitals. The shape of 5 d orbitals are presented here in the diagram. Splitting of d orbitals, the electron lobes in dz square and dx square minus y square orbitals are along the axis and are concentrated close to the ligands, whereas electron lobes in dxy, dyz, dzx orbitals are concentrated in region that lie in between the ligand. As a result, dz square and dx square minus y square set of d orbitals are repelled more strongly by the negative charge on the ligand, and therefore energy of these orbitals increases with respect to spherically symmetrical arrangement, while the set of orbitals dxy, dyz and dzx which lie in between the axes get less repulsion in terms of spherical arrangement of d sublevel. It is therefore in octahedral geometry, the energy of the d orbitals are no more identical and therefore splits up into two sets of orbitals, a set of two orbitals and a set of three orbitals. A set of two orbitals is represented in group theory by letter E and set of three orbitals are represented by letter T. The molecule which are symmetric with respect to center of symmetry is if having symmetric orbitals with respect to center of symmetry, then the subscript G is given that stand for the Girardet in the symmetric representation. But if orbital of some such symmetrical arrangement does not contain any center of symmetry, then the subscript U that stands for un-Girardet have to be introduced. The origin of subscript 1 and 2 you try to find yourself. An octahedral molecule contains center of symmetry, as distance travelled in one direction for getting a ligand is equal when we go in opposite direction to reach another ligand. So, it is desirable to find symmetry of d orbitals in terms of center of symmetry. You can see all the d orbitals are symmetrical with respect to center of symmetry, because when we go in particular direction, the phase of the lobe of the d orbital remains same as and when we go in the opposite direction of this. So, for showing all the d orbitals, a subscript G have to be introduced. So, the set of orbitals here dz square and dx square minus y square which contain center of symmetry can be represented by the representation Eg, and the set of three orbitals which is repelled less by incoming ligand, that is dxy, dyz and dzx, is represented by T2G orbitals. Thus, under the influence of approaching ligands, the 5d orbitals which were originated degenerate in the free metallic cation are now split into two levels, that is T2G level which is triply degenerate and is of lower energy, and Eg level which is doubly degenerate and is of higher energy. The separation of 5d orbitals of the metal cation into two sets having different energies is called crystal field splitting energy. The energy gap between T2G and Eg set of orbital is represented by delta O or 10dq, where the subscript O in delta O signifies an octahedral crystal field. This energy difference, which arises because of the differential electrostatic field applied by the ligand on the d orbital of the central metal cation, is called as crystal field splitting energy. The energy that corresponds to the hypothetical spherically symmetrical environment defines the barycenter of the array of the level. The 2 Eg orbital lying at 3 by 5 delta O above the barycenter, 3 T2G orbitals lying at 2 by 5 delta O below it. These values can easily be determined by following two equations. Let x represents energy of each of the T2G orbitals and y represent energy of each of Eg orbitals. Let barycenter is our reference point, and therefore x will have some negative value and y is a positive quantity. Since the gap of energy between T2G and Eg is represented by delta O, so the energy difference between Eg and T2G level is equal to delta O. Therefore, y minus x should be equal to delta O. This will frame equation 1. Also, when the system do not contain any electron in d orbitals or contain equal electrons in all the 5d orbitals symmetrically filled, then the overall energy should become equal to 0 or should become equal to the energy of barycenter. So, when all the 10 electrons are filled in the d orbitals in the octahedral symmetry, the overall energy of the system should become 0. For each of the electrons possessing in Eg level, energy is raised by the value y, while each of the electron that is occupied in T2G level is stabilized by the value x. So, for the case of 10 electrons, the overall energy will become 4y plus 6x, and this value should be equal to 0. This frames equation 2. Solving the two equations, y comes as plus 3 by 5 delta O and x becomes minus 2 by 5 delta O. So, each of the T2G orbital has zero point 4 delta O less energy than the barycenter, or you can say each electron of T2G orbital is stabilized by 0 point 4 delta O energy, and each of the electron present in Eg orbital is destabilized by 0 0.6 delta O energy. On the basis, let us find stabilization energy for a specific octahedral case. CFSE is the difference in energy between the d electrons in an octahedral crystal field and the d electrons in a spherical crystal field arrangement. We have already seen that the energy of T2G set is lowered by 2 by 5 delta O, while that of the Eg set is raised by 3 by 5 delta O. Now, let us consider a dx ion containing configuration in which P is the number of electrons in T2G set and Q is the number of electrons in Eg set. So, X is equal to P plus Q. Change in energy of the configuration in terms of delta O will become loss in energy due to P electrons in T2G set and gain in energy due to Q electrons in Eg set, that is will become equal to minus 0.4 P plus 0.6 Q energy. Now, since delta O is equal to 10 dQ, change in energy for configuration in terms of dQ can be represented as minus 4 P plus 6 Q dQ. In these equations, we have not considered pairing energy P of dx ion, which we will learn in the next module. But before that, let us solve a problem for better understanding of the concept of the complex TiH2O6 3+ absorbs ultraviolet light at 20,300 cm inverse due to DD transition. Find out crystal field splitting and crystal field stabilization energy for this system, given that 1 kilojoule per mole is identical to 83.7 cm inverse. So, let us solve the equation. In TiH2O6 3+, central metal ion is Ti3+, having electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. Here, d sublevel occupy only one electron. According to above principle, this goes to one of the T2G orbital. This electron of T2G on absorption of a photon of energy 20,300 cm inverse jump to Eg level. Thus, the overall energy 20,300 cm inverse cover the value of crystal field splitting, that is delta O. Therefore, delta O is equal to 20,300 cm inverse, that would become 20,300 by 83.7, which ultimately will become 243 kilojoule per mole. Now, value of CFSE will be minus 0.4 P plus 0.6 Q delta O, where P is the number of electron present in T2G subcell and Q is the number of electron present in Eg orbitals. As you can see here, P is equal to 1 and Q is equal to 0. So, CFSE is equal to minus 0.41 into 1 plus 0.6 into 0. Therefore, total energy will become minus 0.4 delta O. Putting the value of delta O in this result, CFSE will become minus 0.4 into 243 kilojoule per mole, that is, it will become 97.2 kilojoule per mole. Crystal field theory assumes central metal of coordination compound as positive point charge or positive point dipole, and ligand as negative point charge or negative point dipole. The interaction between the two is completely electrostatic in nature. Due to the attraction between metal and ligand, the energy of 5d orbitals first decreases till a certain distance. Once ligand comes closer to the metal, the 5d orbitals of central metal feel repulsion, and energy of all the 5 orbitals increases equally in a spherical arrangement of the ligands. Once the complex makes the octahedral shape, the 5d orbitals feel unequal repulsion, and the 5d orbital splits into 3 T2g orbitals and 2 Eg orbitals with respect to hypothetical situation of energy of 5d orbitals of spherical orientation of ligand. The energy gap between T2g and Eg sublevel is called crystal field splitting. Each of the electron field in T2g has 2 by 5 delta O lower energy than that of the barycenter, and every electron of Eg level carry plus 3 by 5 delta O energy, that is energy higher than that of the energy of the barycenter in an octahedral geometry. The total energy of electrons comes by calculating sum of energy of all the d electrons in a crystal field environment and is called crystal field stabilization energy. In the next class, we will learn about calculating crystal field stabilization energy for low spin and high spin complexes. Thank you very much for listening this lecture.